everybody. Welcome back, folks. Feel free to help yourselves to candy as we progress. I know it's that time of year where every little bit helps of energy, right? More and more people showing up with coffee or, Monster energy drinks, as it were, your coffee of choice. After this, there's only 4 weeks left. I know. Do you know what's good about it, though, is that it's finite. Like, one way or another, it will be over. And everything will be turned in or not. Like, it'll just be done. So, aren't you glad you don't have a final exam in this class? Yeah.
We don't have a project.
Or a project, yeah. You know what? I hate the end of semester projects probably more than you guys do, because it's like there's 20 of them on your desk, and it's like, I'm tired. I don't want to read these. So yeah, I know. Yeah, it's challenging, but I'm trying to dose it so that there's more or less an equal distribution of work. You guys do have a homework that's due during finals week, but it's just a regular homework. So in theory, you can get it done before finals week, and then you're all the way done. So that will be good. There's 2 more. Yep. I still got to figure out how to do them, because I don't think the regular homework system is going to work, because the programs give different answers. So I have to figure out how to do it, but they won't be any worse than the usual in terms of amount of workload. So we started talking about something new last time, remember? Generalized. For those of you who think this stuff is super cool and want more of it, I am actually teaching a course on generalized models next semester, just the single level variant, but I plan to cover those as well as repeated measures variants and path models, path analysis using general models and generalized models. So if you know of anybody who would need to know what Logits and Probits and Tobits and all that stuff are, then tell them to come on down. So generalized multi-level models. Let's go back to the beginning. What are they for? When would you need one? Say that again?
Abnormal data, like the outcome of the binary.
Abnormal data, is that what you said? Or non-normal? Yeah, I like abnormal. That's good. Abnormal outcomes, yeah. Something to where level 1 residuals being normal is not plausible. So binary is one. Categorical, ordinal or nominal, counts, binomials, things like that. We'll talk more about those today, what each of those are. What differentiates a generalized linear model from a generalized mixed or multi-level model?
How many levels?
How many levels? Yeah. So the mixed/multi-level is the one where you have more than one level of sampling, thus more than one kind of variability in your outcome that you have to be able to consider. So yeah, 3 parts to a generalized linear model. First up, some other kind of conditional distribution. What does conditional distribution mean? That smells really good, by the way.
The probability. The probability of something is given something else.
That's one instance in which conditional works, yeah, but there's a different context for it in this case. So I say some kind of non-normal conditional distribution. What do I mean by that? Residuals, the level 1 part. So conditional means specifically after accounting for the fixed and random effects, what's left. That's what conditional distribution means, meaning conditioned after the random effects. As opposed to marginal, which is random effects and residuals put back together again. So we have some other kind of distribution. You'll get a tour of those today as to which kinds would be most appropriate, and we'll have a couple different examples of that. There's also a link function that comes into play. What's a link function? Give me an example of one. Your new best friend. Yeah, Logit or Logit. I will take either one. I think Logit is another one I've heard before. Logit. Ready with me? I'm going to be the conductor. Ready? Logit is the log of the odds of the probability of a 1. Damn it. Yes, the log of the odds of the probability of a 1 is one type of link function. Do you remember another? Just the log. That's another one that people use. What are they for?
One is bounded and then the other is unbounded.
Logit
is unbounded.
Yeah, Logit is bounded on both for outcomes that are bounded on both sides, like probability is bounded by 0 and 1. Log is for something that's bounded on the 0 side but not the positive side. But what are they for? Why do you need them? How do those boundaries play into what your model needs to look like? Stretchy? Yes? Stretchy.
You got stretch them so as they approach the back, they like.
Yes.
Yeah,
This.
Pharaoh walks.
Yeah, it's the walk like an Egyptian. Yes, ask the Google. You can find the YouTube video. I love the bangles. That was one of my first cassette tapes as a young lad. But yes, this idea, because if you have a linear slope for your predictor, right, predicting probability, it's going to keep on going past probability of 1 and past probability 0. That can't happen. The model has to understand that the slope has to shut off. It has to respect the boundaries of your outcome variable. So link functions transform the outcome to be predicted into something that has no boundaries. It stretches it all out. So Logit and probability is one case. Find the picture I want here. This is slide 14 of lecture 5. So this is a mapping of probability on the top of the diagram to Logits on the bottom. The same difference in Logit, so going from a Logit of 0 to 1 to 2 to 3, translates into smaller and smaller differences in probability. So the Logit can go on forever, but it will still asymptote at 1 and 0. So that way you can have a linear slope predict a Logit, because the Logit can keep going on either side. But when you try to figure out what the predicted outcome is from that linear slope, the predicted outcome, when back translated into the original metric, will stay within its boundaries. Back translate, meaning inverse link function, such as the inverse Logit function goes from Logits to probabilities, or in the log scale, exponentiation in that case. So these different units then have a different sort of neutral point. So if you have no idea what's going to happen, whether something's going to happen or not, what would you give a probability of something happening? No idea. What's a neutral probability? 50-50, right? That corresponds to an odds ratio of 1, where the probability of something happening over the probability of it not happening is equal, 1. If you take the log of that odds, you're in Logit land, and that corresponds to a Logit of 0. So Logit 0 equals odds 1 equals probability 0.5. So link function is the other big thing, and then linear predictor is the other piece. That's the part you already know how to do. So those is your linear combination of fixed and random effects, the same as we've been doing all year. And literally all year for some of us. All right. So we ended up here, right? So if we express a linear model on these 3 different metrics, the top one predicts Logits, the log. Here we say it again. The log of the odds of the probability of a 1. Yeah, that whole thing, right? If that's what you're predicting, your linear model looks and sounds exactly like what you're used to. What's an intercept? Not a trick. What's an intercept? Expected outcome when you all need some candy. I know you know this. You got to get that blood sugar pumping. What's an intercept? Expected outcome when the x predictors are 0, right?
Yeah.
You all know that. We've been talking about intercepts and slopes for weeks now. I know you know that. So what do I have to change in order for that sentence to be valid for this beta 0? Expected logit outcome when these predictors are 0. Likewise, what's a slope? Rise over run, change in y per unit change in x, right? So that's totally fine here too. Now what do I have to change about that sentence to make it work for here? Beta 1 is the change in logit y per unit change in x. No logit x, just x. So the transformation that's happening is to the predicted outcome. It's not that your real outcome has been transformed. It's the predicted outcome that gets the transformation. So in this logit metric, intercepts and slopes function exactly like what you're used to, and all is cool. So the right side of the model is super easy to interpret because it works exactly the same so long as you stick logit y in front of y. But then you're left with the problem, what the hell is a logit? And I can drill that into you, it's the log of the odds of probability 1, but you're still like, is that, like, if I have a logit of 2, is that, like, good? Like, what would a logit of 1.5 be? I don't have those things memorized. If you know the logit is positive, though, what does that tell you? Yeah, p greater than 0.5. More likely to have a 1. A logit that is negative, more likely to have a 0. Beyond that, the scale is very squishy because it's stretchy. So whenever we're shopping at a store where the prices are sort of loosey-goosey, we refer to them as being priced in logits. So like, any of you shop at Kohl's? That's a good one for this. There's others, so like the half-price store, it's called Richmond Gorbin's. There's another one that does that. So I'm at Kohl's like all the time. I'm one of their best customers, sadly. And they keep reeling you in because every time you go there, they give you Kohl's cash, right? And then you have to spend the Kohl's cash the next time you go, and it's like, well, I have Kohl's cash for $5. Am I going to leave that on the table? Or am I going to go find something that costs $10 and pay them $5 more? And they get me every time. But I have no idea when I get to Kohl's how much something costs. Because there's a number on the price tag. That number has no bearing on what I'm actually going to pay. Because everything is always on sale at Kohl's. Always. There is no such thing as regular price. And then, even if I were to take 20% off, then I go into my Kohl's app, and I have like another 20% off plus $15 off if you buy this or that. Then I have my Kohl's cash, and then it's like, but I'm going to get more Kohl's cash, so that sort of nets. I have no idea how much these things cost. Like, they're in logits, right? It's like this metric that has no meaning. So much so that if I go over to the little price machine, and beep the tag to check what it costs, I refer to that as the inverse link function because it translates logits to dollars. So yeah, logits is just like the stretchy metric that makes it so that your price can keep getting lower and lower and lower and lower, but that doesn't translate into real dollars. So if you want to translate into real dollars, something that gets closer then is odds, right? Take the log off. Then you're an odds metric. So if I said you have an odds of 3, what does that mean? I know, but what I do know is that means more than 50-50, right? Because it's above 1. Now, what's the smallest that odds can be? 0. So what's weird about odds to me is that you can go from 1 to positive infinity a range this big to describe the probability somewhere between 0.5 and 1, but the probability of less than 0.5 down to 0 is shoved in between 0 and 1. So it's asymmetric and weird, and I can't handle that. So you will see me jump right on over odds because I just can't handle that, down into probability. Probability is like dollars. People know what that means. If I said there's an 80% probability that I'm going to forget my candy, you know there's a good chance that I'm going to forget my candy, and it'll still be sitting here, maybe, when we come back next week. But then when I want to try and talk about what does beta 1 mean on my output in terms of probability, maybe you guys can, but I can't. I can't figure out how to talk about beta 1 when it's wrapped up in this function. By the way, this is the inverse logit link right here. E to the model over 1 plus e to the model. That's how you go from logits back to probabilities. This equation simplifies to the one below. And this distinction, by the way, how these things are written, follows in other areas of statistics too. So if you take item response theory, which is latent variables that predict binary and categorical outcomes, the models are almost always written like this. They predict the probability directly. But if you estimate the same model from a factor analysis literature point of view, it's written in the top, and it's called item factor analysis. There is a one-to-one mapping between the different versions of the models, but it's hard to see it. So that helps to make this area of life complicated. So given that we know what to do with the betas when they're in this framework, what you're going to see me is use the top one. That's how I'm going to write the models. How I'm going to show pictures of the models, though, is by translating logits back into probabilities. Okay, with me? Have some more candy? Anyone? No? Okay.
I have a question.
Yeah.
So if they put the like the X represent gender, so if I want to see whether there's gender differences on the binary outcome, could I just say the out like if putting the out is 1.3, should I say like one gender is 1.3 more likely than the other genders to choose the answer 1?
Yeah, this is honestly something I should know off the top of my head, but I don't. How to put odds in a sentence correctly. Because I know it is multiplicative. Like they're 3 times as likely if it's the odds are 3 or something like that. I think if it's 1.3, it'd be 1.3 times as likely, but I'm honestly not sure without looking it up. Because I can't, the multiplicative thing and the asymmetry, like I can't wrap my brain around it and it's not useful to me. But I think you're right. So unless anyone else wants to help, how to interpret odds ratios? Odds don't exist in IRT either. That's the other reason. Like this whole section just gets skipped in those models, so I'm out of practice with it. But what's not on this page? Error. Where'd that go? Does it mean that our model is perfect? No. Why is error not on my page anywhere? Error meaning the little e at the end of the equation. The little e meaning the idea that there should be residual variance in the prediction, leftover variability in the outcome. Where'd it go?
Once you have the probability, you have the variance.
Yep.
You have the error.
Once I have the predicted probability, I know what the variability around it must be. The variance of a binary variable is the probability of a 1 times the probability of a 0, the end. So not only do I know what the variance around the probability must be, I know that it differs as a function of what the probability must be. It's non-constant. So it's not there. It's not there not because there's no error, but because error is known. It is a deterministic function of the mean in the Bernoulli distribution that we use for these things. Now, we asked you to think about this last time. Not having residual variance changes some stuff, right? Like, what do we use residual variance at level 1 for in multi-level land? I can think of two things off the top of my head that we talked about last time. Like, if you do an empty model, right? Why would one estimate an empty model?
You want to partition the level 1 and level 2 to something.
Yeah, to partition the variability in the outcome to how much is level 2 between something and how much is level 1 within something, right? So how does not having a residual variance affect that process? We don't have a number that's constant to put in the denominator. Right? The assumption of the empty models we've worked with so far is that within variability is the same across all the level 2 units. That's why you can only have one number and call it good. Likewise, the level 2 units are just as equally dispersed as each other. They have the same variance across them and their intercepts. So this difference in what error can be is the beginning of a difference in interpretation from what is known as data scale or model scale. This distinction is not relevant up until this point. But it has to do with whether or not what you're talking about is the probability, data scale, or model scale, which is Logit. We can still calculate interclass correlation and model scale, so long as we are willing to adopt a scaling method that goes with the link function. What the hell does that mean? Well, there's a concept that gets used to describe this that I stole this picture from Wikipedia to try and illustrate. It's the idea of a continuous underlying variable. Ystar is often used to denote this. Have you heard of this before? This idea? It's as if you don't really have a binary outcome. Like in reality, what you have is a latent variable that's continuous. And you just did a crappy job measuring it. You collected the binary version, but really it's underneath it. Like if I had 0 is alive and 1 is dead or something, what I really have is like susceptibility to mortality, right? Something that's truly continuous. Now that doesn't work for a lot of binary variables. Like, do you have a dog or a cat? I have a big cat that barks. I don't know what the middle ground would look like for that. But if you're willing to say, yeah, I have a latent variable, for real. I just measured it crappily. Okay, cool, I can work with that. See, your latent variable follows the logistic distribution. And you can estimate a threshold that describes where you're cutting this distribution up. And you can borrow the variance of the logistic distribution, which is pi squared over 3, to describe the variance of your Logits. So the Logit metric is your pretend continuous underlying metric that you're working with. And if you buy that, and you're willing to borrow the logistic distribution, its variance is pi squared over 3, which is basically 3.29. So in Logit land, in model scale, from here on out, whenever you're using a Logit link, you can swap out level 1 residual variance as 3.29. Problem solved. Now, if you try to come back down to probability, you're SOL on that. It's not going to work because you're in model scale, 3.29. No problem.
But if I add additional, fix it back to the error variance is still fixed.
Yes, it is. So if you estimate the most awesome model ever, and you have within level 1 predictors that are truly awesome, and they do such a great job at capturing your level 1 residual variance, how much do you have left? 3.29. No worries. The model fixes itself for that. This is coming later, but what ends up happening is that the rest of the model has to change scale for this to become the variance left over. That's what's going to happen. I can give you another example using Kohl's on the basis of this. So let's say that you're the manager at Kohl's and you have a pile of sweaters that you want to get rid of. And in order to make any kind of profit on the sweaters, you have to take $25 from each. Like they're the really nice, like high-end Kohl's sweaters, right? So let's say that what you do is you put a price on the sweater that says $50 and you put up a sign that says 50% off. And some of the sweaters get sold. But then there's a whole bunch left and you're like, okay, well, I can't take less than $25. I know, I'll change the price tag to say $100 and put up a sign that says 75% off. Still $25. That's what happens here. The model is in regular price. If you had, say, I'm trying to do the math here. It'd be like if I had a random intercept variance that was like 10 in the empty model and the Logit variance was 3.29. If I explained like half of the Logit variance, my random intercept variance would have to go up to like 15 or something, because it would have to be like, what would the random intercept variance have been for there to be 3.29 left and whatever was just explained? The model scale changes. Whenever residual variance should have been explained but it can't, everything else has to go up to look like what it would have been with extra variance in it. Regular price. So this means that pseudo R-square for level 1, not a thing. It doesn't go down. Everything else changes around it because it can't go down. So sometimes, when you see multi-level models, or even single-level models, you will see the variance here in the underlying variable set to 1 instead. Because that is a different pretend underlying distribution. That is what you get if you do Probit instead of Logit. You think I'm making up all these words, but I'm not. Probit is another link function. It does the same thing as Logit, but on a different scale. A probit is a z-score. Do you remember in your very first stats class, like in the back of the book, there was some tables where you could convert like z-scores to probabilities, area under the curve and all that crap? That's Probit. Probit is the area to the left that corresponds to that probability. So if you have a probability of, let's go 50-50, what z-score does that go with? 0. If I have a probability of, say, 0.90, no, wait, hang on, do it the other way, 97.5, there we go, 0.975, what z-score does that go with?
2.
Yeah, 2-ish, right? 1.96, I think, exactly, right? So instead of predicting in Logits, you can predict in Probits, and that's the z-score that goes with the probability. What's the highest a z-score can be? Infinity, right? Can you have a z of like 27? Sure you can. Not very likely, but it's possible. Can you have a z-score of negative 27? Sure you can. Not very likely. So in the same way that Logit takes probability and stretches it out into something that's continuous, Probit takes probability and stretches it out into something that's continuous. The difference is the variance. If you use a Probit model, what you're saying is that your pretend underlying continuous variable for your actual binary outcome has a normal distribution instead of a logistic distribution. So then the variance of your Probit is 1 as the number that cannot go down, whereas in Logits it would be 3.29 that cannot go down. But here's the thing, as the title indicates, Probit versus Logit, should you care? Probably not. Probably means probably, by the way, in Midwestern vernacular. Because you know what? These things are pretend. Excuse me, latent. Latent means pretend, okay? It does. You don't know what it is. All you have is a pile of zeros and ones. There is no way to say what the pretend underlying distribution for that is. You don't have the information. It doesn't matter what you say that it is. We just set up a model in which we give the scale of the model a basis in either the normal distribution or the logistic distribution. And to get back and forth is a transformation of roughly 1.7. So if you take Probit model coefficients and multiply them by 1.7, you get Logit model coefficients. And here is the mapping of predicted Logits and predicted Probits across probability once they're transformed. Do you see the tiny little difference between the red and the black? No? Me neither. So yeah, they basically map onto the same thing. So you already know about Probits if you learned about ogives in IRT, natural ogive, that's Probit. Versus log odds, like 2PL, 3PL, all that, that's logistic. So that's another link function. Historically, I think Probit came first, but it's really hard to figure out what the probability is that goes with Probit. You have to be able to do the area under the curve, and so someone figured out that you can do Logit instead and get very, very close, and so that's what's used now. Different methods of estimation for these models sometimes force you into choosing one versus the other. So for instance, if you use full regular maximum likelihood, you can pick between Logits and Probits as your scale. Whereas, such as an M+, if you do diagonally weighted least squares, what is it called in R? WLSMB? No? What is it? The one, Levon does that, I think? Yeah. So, limited information for binary outcomes forces you into Probit. So you just have to know what your scale is to know what the model coefficients mean. So Logit, Probit, both of them have this feature of symmetry. The curve increases at the same rate above 0.5 as it decreases away from 0.5 towards 0. So the S-shaped curve is symmetric. That is not the case for two other link functions that you may hear about. So I introduce them here because these are options in your software as well. Log-log and complementary log-log. Those two paired together always make me sort of giggle. Because if you say that, like, well, this is the complementary log-log, and like, what's the other one, the crappy version? Like, it's the non-complementary rude log-log? But no. I think log-log came first, and then they invented the opposite, and so they called it, well, this one's complementary. Not free, but corresponding. Neither one of these is free. So the Logit is the blue line here, and the Probit is the purple dashed line, which is converted from Probits to Logits. So blue and purple are right on top of each other. That's why you can't see them, just to remind you that it doesn't really matter which of those you pick. The others are not. So log-log is the red line. That one maps onto Logits and Probits for probability greater than 0.5, but it slows down as you get to probability of 0. The green one, complementary log-log, does the opposite. So the green one, complementary log-log, is supposed to be better for data in which there's a lot of zeros but not a lot of ones. And red is better for data in which there's a lot of ones, not a lot of zeros. I have played around with these a little bit. I do find they give different answers across these different versions of the model because of the difference in the link. From what I understand, you can use AIC and BIC to decide which one matches better. So long as you're within the same conditional distribution, you can decide which of the links is a better fit for your data. Okay. All right. How are we doing? Fun, huh? I'm not convinced. Molly, you're not even pretending today. Yay, she says. Do you want some more M&Ms? Okay. Let's take a candy break, everybody. You can either mindfully or unmindfully chomp your M&Ms.
Spark straight down the throat.
Yeah, correct. That's unmindful.
Thank you.
Hey, I used to run through it.
They have a fun little happener in Donna this spring.
Oh, yeah. What month is it?
April.
Okay, that's a decent time. Candy? Oh, jeez, you got real food. You can eat it in front of us, it's okay. We're well past lunchtime. Anyone else? Candy? No? You good? Ladies, candy? No? Okay. All right. Candy break over. So this is like a survey of all these things here. We're going to do a Logit one. Proportions. So proportions use Logits too. Yes, thank you. She's giggling. 2 Logit to quit. Yeah. So I'll have to explain this to some of you, but MC Hammer, are you familiar? Like you can't touch this? That video? So he had another song called Too Legit to Quit, and it had hand gestures with it. Too legit to quit. And so I had to take that and say this is too legit. Too legit to quit. That joke kills with the Gen Xers. But I keep dating myself in my cultural references. I have a link to the video. Here it is. So we may have to get that out next time because it's a 15-minute masterpiece. Okay, it's just out of control. But yeah, too legit to quit. So Logit's also used for binomial outcomes. So if you have something like proportion correct, what's the worst you can do on a test in proportion correct? 0. What's the best you can do? 100%, right? So the same boundary problems, same idea. The difference is that there's stuff in the middle. Like you can't, if you have binary data, you have a 0 or a 1. But you can have a proportion of like 53% correct, right? Or something in the middle like that. So you can use, rather than the Bernoulli distribution, which is only for binary outcomes, you can switch to binomial. Binomial is just like Bernoulli, except that it factors in the number of trials. So the total possible basically is multiplied in here to create a mean. So this is what the blue thing here is, a binomial distribution. If you had a mean of 10%, most of the people are on the low end, very few people coming off of the low end. The middle one here, red, is a mean of 50%. Looks kind of normal, looks symmetric. And green is a mean of 90%. So if you have proportion type data like this, rates, where you have to correct for the number possible, you can use Logits as your link and pair it with binomial. In our class website, I gave you a link to an example that I had built for another class that uses binomials. Let me find that here in just a second. My internet always runs really slowly while I'm streaming. Go figure. So I have some information here about code that you would use in Stata or SAS. One extra thing you have to worry about for proportions is something called overdispersion. If you have a picture that looks like this here, let me go back to this, like blue. So if most of your people do very badly on a test, the mean is 10%. That doesn't preclude that some people do really, really well, right? So if you have sort of a skewed distribution with a tail that extends longer than it should, that's called overdispersion. That's where the mean is greater, the variance is greater than what the mean thinks it should be. So the same thing happens in count data. So we'll have an example that I built for you looking at ways to solve that problem. You can do it either as additive or multiplicative. The example that I built for binomial data, it was a longitudinal example. Yeah, here it is. So bonus example for binomial longitudinal outcomes from another class. This was looking at growth in a % outcome over time. So that was the context of that. That had overdispersion as well. All right. Too Logit to quit, categorical data. Logit also shows up in categorical data. The only difference is how it works. And this is, I have an example of ordinal data from the same class, the one before. So there's 3 kinds of category outcomes that you might use here. If you know that they're ordered, ordinal outcomes, cumulative logit. If you're not sure if they're ordered, but so maybe parts of it is, that's known as adjacent category logit, otherwise known as partial credit. And nominal would be generalized logit. So all of these things work the same way. They take a categorical outcome and they divide it into a series of binary outcomes that I refer to as like submodels, and they predict each of those at the same time. The difference in these 3 types of links is how they make that binary variable division. So the one that is most common is what's known as cumulative logit. So that's for ordinal data. This is known as a proportional odds model. You hear that phrase? It's also a graded response model in IRT nomenclature. What it does is divide the ordinal categories into a series of cumulative submodels. So if I had 4 possible categories, what the model would do is predict in one submodel 0 versus anything else, 0, 1 versus anything else, 0, 1, or 2 versus anything else. And I have this color coded into red versus green because whether it's predicting the logit of something greater or the logit of something lesser differs by software. Remember how I told you that software sometimes predicts the 0 and not the 1? Same problem here. So you can have an empty model, for instance, submodel 1, if you make it so that it's predicting the 1, basically the colors, the red is the 0 in each of these models, and the green is the 1. So it's a series of binary outcomes where every category gets used in every submodel. So the first submodel predicts the logit of y greater than 0. The second one would predict y greater than 1. The third one would predict y greater than 2. You have to work between them to figure out what the probability of any one category is. So if you want to know what is the probability of like an answer of 1 specifically, you have to take the prediction from submodel 2 that includes 0 versus 1, 0 and 1 together, and subtract this one that differentiates it. So then the unique part is 1. And the same thing would happen for 2 from the difference between 2 and 3. The first model gives you 0 all by itself. The last submodel gives you 3 all by itself. But anything in the middle you have to subtract between to get it. So it's what's known as an indirect type of model for that. So this one is by far the most common. I kind of hate it. I have very strong opinions about statistics. I'm not afraid to be like definitive. I hate it because it makes a really unrealistic assumption that is almost impossible to test in software, the way that it's set up. And it's this idea of the same slopes across submodels. So for instance, if I throw in a main effect of X, a main effect of Z, and an interaction term into my model, it gives me a different starting point for each of my submodels. So what is the probability of a logit greater than 0 or 1 or 2 when all of my predictors are 0? It starts me off at a different point. But from there, the effect of a 1 unit change in X is the same whether I'm predicting a logit of y greater than 0, y greater than 1, or y greater than 2. So it goes to all this trouble to separate out these submodels, but the default is that all the slopes are the same across them. So it doesn't matter if you're predicting 0 versus 1, and then 1 versus 2, and 2 versus 3. X predicts it to the same extent. And so does Z, and so does everything else. And so do the random effects, by the way, in multi-level models. So that's sort of crazy. It's hard to test it. But people do this all the time and they don't blink. To me, if you have data that are categorical, It's not enough just to give them different intercepts. You'd want to test for the potential for different slopes as well. The other two you will see less frequently. I'd say Logit nominal is the one that's probably the next most frequent. This is what's known as baseline category or nominal response models in IRT land. It's like dummy coding your outcome. So it does the same thing. It takes a categorical outcome and divides it into a series of binary submodels. But the way that it does it is far more intuitive. Like if I have 0 as my reference category, the first submodel gives me the logit of a 1 instead of a 0. The second submodel gives me the logit of a 2 instead of a 0. And the last one gives me a 3 instead of a 0. And all the intercepts and all the slopes are estimated separately across submodels by default. So you can kind of fit a nominal model against the previous proportional odds model to see if different slopes matters, but it's not a direct comparison in most cases. Okay. So that's your brief tour of binary, categorical, and binomial outcomes, all of which use logits in some capacity or another, which is why they're grouped together. How are we doing? Good? Okay, now the fun part, the multi-level part. How does all this stuff affect what you've learned in multi-level? It affects some of it, not all of it. So the things that I've been harping on all semester, like no smushing, still no smushing in these models. Even if you have a binary predictor, it can have variance at higher levels. A binary outcome can have variance at higher levels. That's all the same. The idea of probing interaction terms for simple slopes and talking about like regions of significance or what the slope is for each group, all the same. Estimate statements to do it, all the same. All that's the same. So the linear model aspect, all the same. What does fixed mean? Like a fixed effect versus a random effect? What does fixed mean? Everybody gets the same, right? All the groups share a slope. If I have a random slope, what does that mean? The groups have different slopes. There's a variance in the slope across groups. All that's the same. How do I test for new random things? Not a trick. How do I test for like new random slopes and stuff? Log likelihood difference or likelihood ratio test? That's the same. How do I test for the significance of fixed effects? Stare at the p-value that shows up next to them, the wall test. That's the same. Now, things that aren't the same. Denominator degrees of freedom, not a thing. So you know how in Stata you had to write small to get the f instead of chi-square and t's? That's gone. They don't have that. Remel, not a thing. That's gone too. Everything is regular flavor maximum likelihood. There's a few other things. Estimation is way more challenging. That means that if you were to run models, you're going to have to sit there and wait for them to finish. There was a student working on a 3-level binary model, and I think he was telling me like he spent like a whole day like letting it run on his computer, like each model.
How do you know it's wrong?
Huh?
How do you know it's wrong?
Because the little thing spins and it like says, you know, proc glimix is running, and then just sits there. So troubleshooting these things can take a while. What I always recommend though, because these things take forever, is to temporarily take out the random effects. Take out the random effects until you get your estimate statements right, you get everything like the code working the way you want it to, because it will run like that without anything random. Then once you know that your estimate statements are working correctly and all that kind of stuff, then turn the random effects back on. Okay, so here is a multi-level empty model for a binary outcome in Logits. It looks remarkably familiar, doesn't it? But what's missing in level 1? Error, because it's 3.29. If you're in Logits, if you're in Probits, it's 1. If you're in log-log or complementary log-log, it's some other random number that I don't have committed to memory. If you want to compute an intra-class correlation, you stick your scale, your 1 or your 3.29, in where the residual variance would go. It is a model scale intra-class correlation, though. You cannot talk about probability with it. You can only talk about logits. There's an article on your reading list. It was the first time I'd ever seen someone tackle intra-class correlations for not besides binary, because this is a thing that's specific to binary. What it would be for some other type of distribution, I had seen everyone else punt on it. And I finally found an article that tackled it, and that's why you have an article from like Ecology that's talking about like trees and shit, because that was like, it's like trees nested in forests or something. So it's still No, I'm serious. Like it's like from a completely different context. I'm not even sure how I found it, but they actually not like literal trees, like the trees that grow in the ground trees. I'll pull it up here. Let me find I'm just telling you, like it's way out of like what I would normally read. Let me see. It may not be trees. Let me see. Evolutionary biology. So they're talking about phenotypes and repeatabilities. That's intra-class correlation. So they have examples that have to do with like fish and trees and stuff like that, right? But it's still clustering. But these people are the only ones that I've seen actually tackle this. Everyone else I've seen punt. So anyway, so this stick 3.29 in there and call it good is only for binary. Interesting story. So I'm going to show you one for a negative binomial. And I read, it was Walt Stroop's Generalized Mixed Models book. So he's a person in the stats department at Nebraska when I was there. And I read his book. Actually, I read it on vacation one year. I read it at the pool because, you know, I'm quant cool and that's what we do. Some woman walked up behind me and she looked over my shoulder and she's like, "Are you reading math at the pool?" Yes, I am. That's how I relax. But anyway, he had a binomial example, I think, or a negative binomial, and he stuck a 1 in here to make an intra-class correlation. And I was like, but you can't just stick a 1 in. Like, where did that come from? So when I got back from vacation, I asked to meet with him, and I had some questions from his book. And I said, "Where'd the 1 come from?" He said, "Oh, I got it from this other book." Okay, so I tracked down that book, and there's a 1 in there with no explanation. Okay, where'd that come from? So I emailed that guy, and he wrote back. And do you know what he said? "I don't know why it's there. I found it in another book, but come to think of it, that doesn't really make a lot of sense. I'm not sure what it should be." Okay, so I've like exhausted my supply of smart people to ask this question to. So I was excited to see the article about, you know, random fish in the forest or whatever that, you know, they're talking about this. So just know that what should go here is not well defined or well agreed upon. And so for that reason, in your negative binomial example, I totally punt, and there is no intra-class correlation because no idea what should go here. So it's a long story. Anyway, it's for further research. There's a dissertation topic for you. Prove what should go here for other length functions and residual distributions. I will be eternally grateful if you can figure this out for me, because I don't do math. I just read about it at the pool. Maybe Bayes can fix it, right? Bayes fixes everything. They can figure it out that way.
Keep going, like after the people that developed that, we find like, oh, the guy's dead. Sorry, so we can't get the answer.
Yeah, he died. He took the secret with him. So you'd be surprised, though, if you actually track down the sources of things, how you can like daisy chain back to something that's wrong, that's just been carried forward because no one cited. Like in my dissertation, there was this phrase defining useful field of view. I used to do attention research. It's the idea that like when you're focusing on something, like it's almost like you have a window of things that are within your focus and consciousness, but not everything gets in. And there was a particular definition of it that had been cited multiple times and credited back to this 1970 paper. I went and got the paper. It's not in there. It is not in there. Someone got it wrong like 1 million years ago, and everyone else has been citing that wrong ever since. So what's interesting is when people cite my papers, and I'm like a reviewer, and I'm like, I didn't say that. Like, how do I correct them without coming off like a douche? Like, so half the time I'm like, I'm just going to have to self-identify. This is me, and I did not say that. Like, because I don't want that to keep going, right? And I've done that for things that both they give me credit for things I did not come up with, or things where they misphrased me. So I do it for both. But anyway, check your original sources. That's where I was going with this. I haven't had the candy, I swear. It's just lemonade in here. A little hyped up today. But if I throw a random slope in, the model looks the same, still no E. So there's not a lot that changes in how you write equations or how you think about fixed and random effects. That's the good news. An ordinal model would look like this, where I've written out the proportional odds assumptions explicitly that go with this model. In theory, they should be testable, but doing that practically is very challenging. One thing that is different is what a fixed effect means. So this is a distinction that has not come up yet. It only comes up in generalized multi-level models. So I had told you that the fixed effect is the average effect for the sample, right? So like if I have an empty model, I have a fixed intercept and a random intercept. The fixed intercept is the mean of the group means. The random intercept is how far off that group's mean is from the mean. Cool, right? Not anymore. So there's something called marginal versus unit specific that you have to pay attention to in thinking about your fixed effects. And what it means is that the fixed effects are conditional on the random effects too. So what I would say if I have a fixed intercept and I'm predicting a binary outcome, for example, then that's the logit of the probability of a 1, specifically for someone who has a random intercept of 0. What it works out to in binary data, thank you Walt Stroop for this little tidbit, is not the mean, but the median. The reason is the nonlinear transformation doesn't hold back translate the same way. So if I have a set of data and I take a sum of it, or the mean of the data, and then I take the log of the mean, that's not the same number as if I take each individual observation, take the log of it, and then take the mean of the logs. That's why they don't agree. So you just have to keep in mind that when you're talking about your fixed effects, it's not really on average. It's in the middle of the distribution, conditional on somebody, on a group that has a 0 for the random effect. Now why does this matter? Because you're going to see some strange shit as a result of this. So like if I have an empty model and I have a variable that has a mean, say, of 0.6 for my binary outcome, you would expect the predicted logit from my fixed intercept to correspond to the probability of 0.6, right? That's what the empty model does. It gives you back the mean. But it doesn't. It gives you the mean for an average group. So the fixed intercept will not be the mean of the variable. The other thing that I found out in building your negative binomial example is that software differs in what they give you. So in Stata, for instance, you can ask for lincoms that give you predicted fixed effects, and you can ask for, ostensibly, them to be translated into the original metric, probabilities, counts, etc. When it does the translation process, it marginalizes over the U's. So the two sets of results do not correspond, whereas SAS does not marginalize. So you have to know, based on your output, if you're looking at things that are unit specific, meaning conditional on a random effect equals 0, or marginalized, meaning like if I sort of aggregated over all the U's, this is the value that I get, because they don't match. So that's one extra complication that you have to worry about in these models. We talked about this earlier, but here's the exact translation of how the model changes scale. So when you explain level 1 residual variance, it should go down, but it can't because it's fixed. So this is what happens to everything else. The fixed effect coefficient from a mixed model is related to a fixed effect coefficient from a single level model according to this. So what ends up happening is that every time Residual variance should have been explained, such as by level 1 predictors. Random intercept variance goes up, and the fixed effect coefficients that correspond to it go up as well. So we can do pseudo R-square for level 2, and level 3 and level 4 if you were to have that. We can't do it for level 1. And you'll get to see this in the examples that we do as well. All right. Do you want to see an example? I don't want to talk about estimation today. I'm too hyper. I gotta put that one off. Let's see an example. The good news is that the software looks remarkably similar. I have example 5A here for you in SAS and in Stata. So this is example 5A I'd like to pull out here. This example is admittedly stupid. By stupid, meaning something that you would never do in research. But I don't have a whole lot of clustered data at my disposal. So when I built it originally, it's using the same data that we use for example 3B. So since we're familiar with that data already, it's helpful to see it from the other side. But what we did in that example was take math and predict it from free and reduced lunch, which was binary. I'm flipping it over. We're predicting lunch from math scores. Like I said, stupid, but the math holds. So everything in terms of setting up the code is the same. I'm getting school level means for math and lunch. I'm keeping schools that had more than 31 people. I am going to use group mean centering to look at the influence of math. And I'm also rescaling math by divided by 10 because the scale is so big I didn't want there to be numerical stability problems. So level 1 math divided minus school mean math gives me my new within school math. That's group mean centered. School mean math minus 50, which was near the mean of that variable, is going to be my level 2 predictor. So here's what we end up with, where binary outcome is whether or not a student gets free lunch. That ranges across schools from 0% to 80%. So right there, without even doing a statistical test, I can tell you there's dependency. Your probability of getting free lunch is correlated of people from the same school. So here's the Stata version. Everything looks pretty much the same as before. So first thing here, empty model on empty means single level model. I'm doing this for 2 reasons. One of them is practical. I want to make sure that I know whether this software is predicting the 0 or the 1. The output is going to match one of those. It's going to match either the probability of a 0 or the probability of a 1 from the data. And I'm estimating the single level version so that it matches exactly. So the magic number that we should be looking for, 31. 0.31 is the mean of the binary variable where 1 means you get free lunch. So 31% of the kids get free lunch as the 1, and doing math in my head, 69%, does that sound right? Have a 0? So my output, when I convert Logits back to probability for the intercept, is either going to match 0.31 or 0.69. And whichever one it matches, that's which way it's predicting. Spoiler alert, I already figured this out. I figured out that in SAS, welcome to your new friend in SAS, proc glimmix, generalized mixed models. They put an extra I in here, I think, just to make it read better. Predicts the 0. I said, oh hell no, I can't handle that. So I fixed it. They have this option that flips which one, and that's what descending does. It makes it so it predicts the 1 instead. Stata, ME Logit. Have you got Stata folks, have you seen these before? There's Logit, right, by itself. ME, if you put it in front of it, stands for mixed effects. So all of the generalized models that are for single level, a lot of them, if you just stick ME on it, it will give you the multi-level version. And it works a lot like the mix that we've been doing. So a few new things in here. I have added, importantly here, the model outcome here, free and reduced lunch. That's the first thing here in Stata as well. In SAS, you have to tell it what kind of model you want. So Glimix is a general package that allows you to choose from a lot of different links and a lot of different conditional distributions. So I'm saying link equals logit, dist equals binary, so that I know I'm predicting a binary outcome using a Bernoulli distribution for binary using a logit link. Do you know what you get if you forget these by default, by the way? Any guesses as to what they would default to if you don't say what you want? What have we been doing all semester? Normal. And what do you call it when you don't have a link? You just say, do it. Identity. That means times 1. No transformation. That's what the default is. It defaults to mixed. In Stata, they have an MEGLM that is the analog to Glimix, although it seems like the specific ones have more options that work better with that particular combination. So I'm just going to switch out which one it is based on which model we have. So that'll be the main difference. Glimix is sort of a general purpose, whereas the Stata one, what it's ME of, will switch as the model switches. So estimate has a new option. So why am I writing out I'd like the intercept? Up to this point, that would be like, duh, you're going to get the intercept anyway. ILink stands for inverse link function. That is your magical figure out how much this costs in dollars, takes it back from logits to probabilities or logs to counts. So it unlinks whatever you have to give you the predicted outcome in that more intuitive metric. Stata does not have a direct analog to ILink, but it does have this thing. NLCOM stands for nonlinear combination, as opposed to LinCom, which is linear. So what I am doing is calculating the predicted probability, where underscore B, this underscore constant means the fixed intercept coefficient. I had to look that up. I have no idea why it's this, but this is what it thinks it's called. So then if you do 1 over 1 plus e to the naught model, that's the inverse link function. So that is the analog to that option right here. One last thing, because both packages now are using regular flavor maximum likelihood, their AIC and BIC values will agree so long as you use the right sample size in computing BIC. So I have changed the sample size used to match that of SAS. So since we have 94 level 2 units, that's what S.IC gives you. It gives you AIC and BIC that will match that printed by Glimix. So not strictly necessary, but just one thing that we can now do. We get a lot more fit statistics than usual. Here's my intercept from my empty model, minus 0.8. What is that? How can I have a probability of getting free lunch that's negative? It's a logit. What's logit? Log, the odds, probability of a 1. So the fact that that logit is negative tells us what? Less than 50-50. Otherwise, I have no idea what a logit of 0.8 is. But I'm going to get SAS to tell me. So here is my inverse link function. e to the model over 1 plus e to the model. So this line right here is what the estimate command gave me, where it repeats in Logits the predicted fixed intercept and its standard error. And then over here, this column that says mean, that's your probability. You have no way of knowing that, but that's what it means. And standard error of the mean is the standard error of that probability. So 31%, that is the proportion of students who got free lunch. The model is predicting the 1. Now I know what's up. To add the multi-level part, random, and here's my bar school ID. That part's exactly the same. We'll talk about estimation next time, but just to point out the unit-specific nature of these fixed effects, my intercept used to be minus 0.8. Now it's minus 1.2 after adding in the random effects. That translates into a probability of 0.24 rather than a probability of 0.31. So that's the predicted proportion of students who get free lunch specifically for an average school with a random intercept of 0. That's why it does not match the data. Here's my ICC. There's my random intercept variance. It goes on the numerator, and here in the denominator, here's my magical 3.29. So the intra-class correlation is about 0.37. 37% of the variability in free lunch has to do with which school you go to. So it's like a tendency to get free lunch is what that random intercept is capturing. Some schools have a higher tendency. I want to say propensity, but that's a loaded term that means something else, so I'll stick with tendency. See? Ta-da! Other than the Logits part, and that E is gone. It's just 3.29, the end. It's multi-level again. And now you know why I wanted to offer a class on just the Logit part before trying to throw it into the multi-level part. Because of that together is kind of a lot. So, questions? All right, well then we are out of time. I am going to put up another formative assessment for you to work on before the next class. So no homework right now, just one more of those. I will let you know via email when that is ready. We'll go over it on Tuesday. Otherwise, let me know if you need anything. Office hours start now. Come help yourself some more candy before you go if you like.
I have a question about the correlation.
Yeah.
I never really understand what correlation is. I
This
know, yeah, it's the students in the same school, but what are you measuring that correlates among the students?
Your tendency to get free lunch or not.
So correlation you have to two columns, right? For one column.
It's like student 1's free lunch variable and student 2.
So you have all the pairs and then you average.
Yeah, so if you took your long data set and flipped it to wide, where like since the students are interchangeable, like we don't worry about that, but this would be like student 1, student 2, student 3, student 4, student 5. Like we built a correlation matrix out of those. This is supposed to be the average of those correlations.
So my understanding is between student 1, student 2, and then student 3, but do you get this. I don't get what's the correlation between student 1 and student 2.
Whether student 1 got a 1 and whether student 2 got a 1.
So that would be like the correlation between these
Two binary variables. This is like a tetrachord correlation. If that helps you.
It's just hard for me to wrap my mind around, like you have two numbers and you get a correlation about it.
Well, you have more than two. Right, you have student 1 with 2, student 1 with everybody, student 2 with everybody. Like if the rows were schools, right? Each school has a student 1, each school has a student 2.
Yeah, I don't have that. I kind of feel like it's kind of like the alpha coefficient, like a